This is Bill Farmer again. Welcome back to McMaster University course, Computing and Software 701, Discrete Logic and Discrete Mathematics. We're continuing with the topic of basic mathematical concepts. Today we're going to talk about algebraic structures, Boolean algebras, and lattices. So an algebraic structure is a very common kind of mathematical structure that has a very particular form. We see here it has a finite set of domains like all mathematical structures, a set of elements or values in the domains, and a set of functions over the domains. Usually in an algebraic structure there will be just one domain. So there's many different kinds of algebraic structures. I've given some well-known examples in this slide. And there's many more, many algebraic structures. These are just some of the most well-known. So I'll mention them. A magma here is an algebraic structure which has a domain D and a binary operation which I'm going to call mul. And this binary operation need not have any other properties. A semigroup is a magma, but its binary operation is associative. A monoid is a semigroup which also has an identity element. And a group is a monoid which also has an inverse operation. Now, there's also a whole group of algebraic structures that have a plus operation, addition operation, and a times operation. But these operations are asymmetric. So for instance, we have a ring, a semi-ring. An example of that would be where the domain would be the set of natural numbers. And we have a ring, example of that would be a set of integers. And a field, example of that would be having our domain be the rationals or the reals. And then there's a division ring, which are relatively rare. A division ring is like a field, but the multiplication operator is not commutative. But it does have an inverse operation. So if you think of a field, we have 0 and 1, plus and negation, times, and multiplicative inverse. Now there's also algebraic structures that have plus and times which are symmetric. And I'll give two examples here, lattices and Boolean algebras. We're going to talk about both of these. These are particularly important for computing. Now, the last group I'm going to look at is one group you may be familiar with. That's a vector space. We have a set of vectors. We have a set of field elements. We have an addition, so we can add up vectors. And we have a scalar multiplication, so we can multiply a vector by a member of a field. And then a module is like a vector space, but instead of a field, we have a ring. And an algebra is a vector space where we also have a multiplication operation, so we can multiply the members of our algebra. So it's like a vector space with ability to multiply vectors. Okay, so let's talk about a Boolean algebra. Like I said, this is an algebraic structure that's particularly important to computing. Notice we have a domain B, a 0, a 1, a plus and times, and we have a complement operation, which is unary. Plus and times are binary. And I'm going to give the axioms for Boolean algebra a little bit later, but we call Boolean algebras in honor of the great mathematician and logician George Boole, who in 1847 he presented the idea of a Boolean algebra, and he's really the first to recognize that truth values and how we manipulate truth values is very analogous to how we deal with numbers. So we can manipulate truth values in an algebraic way, much the same way that we manipulate numbers. This was his discovery. Now there are infinitely many non-isomorphic Boolean algebras. There's billions of Boolean algebras, billions and billions. And in computing, probably the most well-known application of Boolean algebra is it's used to model electronic circuits. Here are the two most important examples, I would say. The first example is the one that inspired Boole. Our set of values is just right here. It's just true and false. And false plays a row of 0, true plays a row of 1, and disjunction plays a row of plus, and conjunction plays a row of times, and negation plays the complement. And the other example is where our domain is the power set of some universe. And so the empty set, this is the empty set is 0, the universe is 1, union is like plus, intersection is like times, and the complement is like complement. Okay, so that's what a Boolean algebra is. Here are the axioms of the Boolean algebra. We have associativity laws, commutativity laws, distributivity laws, identity laws, and complement laws. And if you think for algebras that deal with numbers, they have similar ones, but notice these laws are completely symmetric. So for instance, if we look at the associativity law here, in this case we have plus, and in this case we have the same law, but we replace plus with times. If we look at this law, distributivity law, we get the second one by making plus times and times plus. So these are completely symmetric laws. Now, here are some theorems we can prove from those laws. And the laws plus these theorems are basically the properties that people use when they're reasoning in Boolean algebra. Now notice there's going to be I'll just say again that these laws are completely symmetric, which means I can get from one version to the other by changing the role of plus and times. Okay, so let's talk about another topic, lattices. Lattices are extremely important in computing. So a lattice is a particular kind of weak partial order. And this, if it's a lattice, if you have a weak partial order, it's a lattice if your lattice satisfies two properties, which I have right up here, 1 and 2. 1 and 2. The first property is that if I take any pair of elements from my domain L, then that pair will have a least upper bound in L. And we call this the join of A and B. So this property says joins always exist. And similarly, for any pair of elements in L, there is going to be a greatest lower bound, which we call the meet. And so this property says meets always exist. So a lattice is a weak partial order with joins and meets. Now a lattice could have a maximum and could have a minimum. We call the minimum bottom, and it's represented by either 0 or the bottom symbol. And we call the maximum top, and it's represented either by 1 or the top symbol. So I've given some examples of lattices here. This is one of the most common, most well-known examples. We have the power set of a set, and we have the subset or subset or equal relation. And this lattice has both a bottom and a top. The bottom is the empty set. The top is the set S. If we take the natural numbers in less than, it is a lattice, but it does have a bottom. 0 is a bottom, but it has no top. If we take the mathematical structure of the natural numbers with the divides relation, so we say A divides B, that just means what you normally would mean by A divides B. This is a lattice with a bottom and a top. I'll let you figure out the bottom and the top are, but the join is going to be the least common multiple of two natural numbers, and the meet is going to be the greatest common divisor. So this is a very, very interesting example of a lattice. And finally, any Boolean algebra is a lattice. We can think of a Boolean algebra as a partial order if we define less than or equal this way in terms of times and plus. And it's a very particular kind of lattice. It's what's called a complemented distributed lattice. Okay, then there's a notion of a semi-lattice. Basically, a semi-lattice is a partial order where we have joins or we have meets. So either all the joins exist or all the meets exist. So if the joins exist, we call it a join semi-lattice. If the meets exist, we call it a meet semi-lattice. Of course, any lattice is a semi-lattice. And we haven't talked about trees yet, but we can think of trees also as a semi-lattice. Okay, now, one of the interesting things about lattices is the way I define a lattice is it's a special kind of weak partial order. We can also think of lattices as algebraic structures. In this algebraic structure, we have two binary functions. These binary functions are join and meet. And notice that if we have a lattice like this, then these algebraic structures, where we throw away one of the two binary operations, they are going to be semi-lattices. And then a bounded lattice is an algebraic structure like this. It's a lattice, but it also has a 0 and a 1. And the 0 is going to be the identity element for the join operation, and the 1 is the identity element for the meet. So if you wanted to think of the join as plus, that makes sense. 0 is the identity element of plus. If you think of the meet as times, 1 is the identity element for times. Okay, so here are the axioms of a lattice. We have associativity laws, commutativity laws, and absorption laws. And from the absorption laws, we can derive the idempotent laws, which basically say the join of a value with itself is itself, and the meet of a value with itself is itself. Okay, we're going to talk about one more thing today. That's what is it called a complete lattice. So a complete lattice is a weak partial order. But if we take any set of members of L, that set of members has a least upper bound and a greatest lower bound. So you're probably wondering, well, how is this different than a lattice? A lattice is a weak partial order where if we take any set of two members of L, that set of two members has a least upper bound and a greatest lower bound. Here, we can have any number of members, including an infinite number of members. So here are some of the examples. We could have a power set with the subset or equal relation. That's a complete lattice. If we have the real numbers with the open interval of 0 and 1 with less than, that is not a complete lattice, because if I take the whole set and ask for a least upper bound, the least upper bound should be 1, but 1's not a member. But if we add 0 and 1, then it becomes a complete lattice. If we take the rational numbers with the closed interval 0, 1, this is not a complete lattice because it's not complete in a geometric sense. So for instance, we're going to have values that are irrational between 0 and 1, and for that reason our lattice won't be complete. If we take the natural numbers with less than or equal, that's not complete because if we take the whole set of natural numbers, it does not have an upper bound, let alone a least upper bound. But this lattice of the natural numbers with divides is a complete lattice. I'll leave that up to you to show that. Okay, so we're going to stop here, and we will have one more lecture for this topic, basic mathematical concepts, later down the road. Okay, thank you very much.